Swayam Prabha. Digital India. Educated India.
Let us take another example. So, let's take okay, I have to get the pen. Let us take an arch like that with a pin joint there, another pin joint there. How many segments are there? We have fixed frame, that is one segment, and then two here. Now, if we do degrees of freedom for this, 3 times 2 minus 1, we took care of that, and then kinematic joints we have 2 pin joints, that will be minus 2 times 2. There are no compliant or elastic pairs here, and there are no fixed connections. So, these two are not there. And now we come to the last one. If I take, because I do not know what to take segment compliance for this arch, so I take 3. When in doubt, we take the full one, then it will become 3 times 1. There are no other elastic segments here, only one. So, if I do this, this is 3 minus 4 and then plus 3, that gives us 2. There are 2 degrees of freedom. We can interpret because there are 2 joints here. So, I can apply a torque there, I can apply another torque there. So, 2 degrees of freedom can be explained. Now, let us take a small variation of that. So, we take the same arch and let us say that now I am applying a force here. Okay. Now, what happens to count the degrees of freedom? We have basically not introduced any new segment, we introduced a force. That means that when I have an arch like this, I have 2 degrees of freedom, which we have already indicated as 2 torques here. There is this 1 degree of freedom, another degree of freedom, but now I am saying in addition to those, since it is an elastic segment, I can apply an additional load here. That means the degree of freedom has increased. So, that is what the confusion to say that if you have elastic segments, you can apply as many forces as possible, and hence there are infinite degrees of freedom. But that will be incorrect and also confusing. So, what we say is that whenever there is a force acting, we will introduce that there is kind of a virtual rigid segment, okay, virtual rigid segment. That is virtual in the sense it is not there, but we use it for our convenience. Then the degrees of freedom formula holds. We can also interpret as to how many are there. When there are not any, like in this example, there are only 2, there is no question. The moment we have a force, at that point we introduce a virtual rigid segment. Okay. When we do that for this one, so I have now this segment where I want to apply the force, and then this we can work it out, saying that we have 1 here and then the 2 virtual rigid segment, we have to count that. Now, that has broken our elastic segment into 2, there is a third and 4, right. Now, if we do degrees of freedom formula for this one, so we have 3 into 4 minus 1 minus 2 joints are still there, that is 2 times 2. There are no compliant ones, that is 0. Number of fixed connections, there are no compliant pairs, that is all 0 here. And then fixed connections 3 times, we have 1 and 2 here. So, that is 3 times 2. Okay. Segment compliance, again when in doubt we say segment compliance of 3, there are 2 such things, that is segments 3 and 4. Let us see what comes out now. This is 9, 4 minus 1 is 3, 3 times that 9 minus 4, and then this is minus 6 and then plus 6. Okay. So, what do we get? 9 minus 4 5, 6 and plus 6 minus is cancel, we have 5 degrees of freedom. Where are the 5 degrees of freedom? 5 degrees of freedom, like what we had before, we have this torque, that is 2. Now that we have a rigid body in a plane can have 3 actuations, x force, y force and a moment. Okay. Again 5 comes out fine. So, wherever there is a force, we introduce this virtual rigid segment, so that we can interpret degrees of freedom, meaning that again it can have maximum 5 degrees of freedom. In this particular one, if I give only this torque, it will move deterministically, only this one it will move deterministically, both of them it will move, or any number. So, that is 5 degrees that we identified, any number you apply from 1 to 5 it will give you deterministic motion. That is a characteristic of the degree of freedom formula for compliant mechanisms. Now, let us take an example report in the literature called an elastic arm. What you have here is a flexible beam, and there is a cable that goes over a spool here like a winch, and then there are the motor or this thing has a kinematic joint, We have shown it with virtual rigid segment and without it. Okay. This is a VRS over here, this is a VRS over there. Okay. There is one here virtual rigid segment and there is another one. Let us look at this formula computed both ways. Number of segments here in the first case A, that is this one, we have 4 segments. There are 2 fixed connections. Where are they? There is a fixed connection between 2 elastic segments and the last segment and the spool, and we have NK12 that is over here and over here, NAC3 2 because I have the flexible beam as well as a cable, like when we in doubt we take it as 3. If we do that we get 5 degrees of freedom. How do we interpret this here, 5 degrees of freedom? It is clear that I have 1 degree of freedom there, another degree of freedom here, right. But what about the other 3 that it formula gives? That is where we have to say, when we are taking an elastic segment and another elastic segment, when they both are connected like it is happening here, it is useful to have virtual rigid segment. When there is a pinch joint to the ground, you can take it or not take, that does not matter, but it is useful whenever elastic segment is connected to a rigid segment, another elastic segment, taking a VRS virtual rigid segment makes it easy for our analysis. If we do that, by adding this VRS over here and over here, number of segments increases to 6, from 4 to 6. Number of fixed connections also goes up to 4 because we have 2 additional ones that come there and here between VRS and the flexible beam, VRS and the rope, the other ones over here. So, we have that, and then the earlier whatever we had, that is still there. Okay. So, number of fixed connections has gone up and number of kinematic joints remains the same, the same old things, and NSA3 elastic segments are still 2 with segment compliance 3, we have that. If you calculate, again it will give you the 5 degrees of freedom. Now, it is interpret in the sense that we have 5 degrees of freedom that we can have as rotation over there and then rotation over here, 2 torques, and then since a virtual rigid segment, I can have force in the x direction, y direction and the moment on it. In fact, this elastic arm has at this point a robotic hand attached to it, that is an end effector that can have 3 degrees of freedom, and then you have 2 torques, and that is how it works out. So, we can interpret the degrees of freedom, and you see now 2 cases where you would use virtual rigid segment. One is wherever there is a force on an elastic segment, and the other case is whenever 2 elastic segments are attached to one another or an elastic segment is attached to another rigid segment. We put virtual rigid segment, then interpretation becomes easy. So, in the case of A, when we got 5, we did not know how to interpret the extra 3 freedoms other than the 2 torques here. The moment you have virtual rigid segment, then we know that at that point we can apply 2 forces and a torque. Once we have this, if I take a compliant mechanism such as that, we can see that there is an elastic segment here and here, and then there is this one which is attached to this. Okay. We can interpret that as a VRS there, that is shown there, and then another segment and another VRS here, because this mechanism where you apply force in that direction and this gripping action happens here. So, there is a force, you take a VRS and then you take another segment, and of course, the symmetry you have this. So, in this particular case you have number of segments 8, number of fixed connections 8, that is 1, 2, 3, 4 and then 4 more, and NSC1 we are not taking any, we are taking NSC3 as 4, the segments 8, 6, 4 and 2. Okay. Degrees of freedom then come to 9. Since there are 3 virtual segments, each of them can take 3 degrees of freedom, we can say it has total 9 degrees of freedom. But looking at this particular gripper, you think apply a force is only 1 degree of freedom. If you want to do that, then we have to make a little change as shown in this case B. The case B, we are saying that instead of NSC 3 being 4, you are saying that NSC 1 is 4. Okay. That means that each of these segments have segment compliance only 1. What does it mean? In this particular case, these segments only bend, they do not stretch or move in 2 dimensions. Now, when you say a segment in planar case has 3 degrees of freedom, it can bend in more than one way to cause x and y displacements and a rotation possibly, right. Those are the 3 freedoms. You say that each of them simply bends only one mode, in which case you take segment compliance 1 here for each of those, then you get degree of freedom 1, and that is how we can interpret it. So, we have to have a little understanding of segment compliance depending on the situation. So, when you take a complicated case such as the one shown here, which I have a real mechanism of what you see on the screen, where you apply force, we had seen that earlier. So, it is going to move for this portion, for this mechanism. So, if you want to do it, there are too many beams here, okay. There are a lot of beams. When you have so many beams, you can not keep on counting each one of them. Instead, what we say is that all this thing is more or less rigid, and so is this little portion, and so is this portion, and so forth, and so is this. The whole thing can be one rigid segment. That is what we have shown our interpretation here. Okay. Let us go back to the slide and then interpret this entire thing as one rigid body, this as another rigid body, this portion is another rigid body, and then this one as another rigid body, and then interpret. And then we have elastic segment there, elastic segment here. These two are elastic segments. Okay. With that interpretation, we can count the degrees of freedom. Counting is the strength of Grübler's formula. So, here if you do, we have 1, 2, 3, 4, 5, 6, 7, 8 segments when you do the calculation, and between segments 1, 2 and 2, 3 and then 3, 4 and then 1, 8, we have flexural pairs, right. There are flexural pairs over here, and the way we have shown over here between that and this, and then over here there are 2 between this and this, that is this and this, this and that, as shown in this one over there. And then we have fixed connections also between 2 and 5, 4 and 6, 5 and 7, 6 and 8. And then NSC 3 we have taken 2, that is segments 5 and 6. Again, in case of doubt, you take the full. So, we have 2 such things. If you put that into the formula, which you can check slowly, we get 5 degrees of freedom. When you have 5 degrees of freedom, we can actually count them. How do you get 5 degrees of freedom for this? It is supposed to be the force you apply here, this moves in that direction in amplified way, that is clearly 1 degree of freedom, but then nobody prevents you from applying a force in that direction, and movement also you can hold it and rotate, those are 3 degrees of freedom. After that, since we have the output here, we can also apply a force over there, and we can apply a force over here. What it tells you is that then you cannot apply, I will put that in a different color, if it tells you that there are only 5 degrees of freedom, then you cannot do this independently. That, or because you have flexural one, you can also apply those blue ones you cannot. When you do that, you will have to disturb the other degrees of freedom over here. The red ones that we have written 5 degrees of freedom, that is a maximum freedom possible for this mechanism, then you cannot do this. When you do that, when you apply a torque at this point, let us say this joint, if you apply a torque there, you will be holding at an angle. If you hold at an angle and try to apply these blue actuations, it would move, and that means that whatever you have specified before now will not be valid, and that is what this number says. So, compliant mechanisms, however complex there will be maximum degrees of freedom for it as predicted by our formula. So, this is our degree of freedom, that is a maximum possible for this is 5. So, once you specify, well, we have 8 possible freedoms here that we can apply. Out of those, only 5 can be applied independently, other ones you cannot independently do it, because then you have to disturb the remaining, the first 5 that you have applied. Okay? That is something we can understand by simply counting. We can take the example of a compliant stapler that we had seen. So, here there is an abstraction that is shown as the frame 1, and then top portion of this S2, and then there is a elastic segment 3, and then this block 4, and then lower one where we hold the staples, that is 5, number of segments is 5, fixed connections you can see where they are, that is 1 over there for this one, it goes to the other side. So, there is this. Okay. NK1 we have a kinematic joint which is a slider here, okay, that is the slider, 4 moves relative to 5, and then we have NC1, there are 2, these are the flexural things, right, these are the flexural or elastic pairs, we have 2. NSC3, the last segment that we have is 1, if you do that, degrees of freedom turns out to be 3. You can interpret that, meaning that I can have one freedom there, another freedom there, and I can move this block. Okay, those are the freedoms. So, you can interpret degrees of freedom for anything that you like. And we come back to Rolomite, and here we have shown that number of segments are 4. We have top one and the bottom one is fixed frame, okay, that is the same thing, and a flexible metal is 2, that is strip, and then the 2 rollers, those are the 4 segments. And in NK1 you can see what revolute joints we have, 2 rollers, and in NC3, that is flexible metal, has segment compliance 3, one such thing. N fix, where it is fixed, we have 2 of these fixed connections. In fact, fixed connections are literally shown here with bolted connections, fixed connections. If you do that, degrees of turns out to be 2 for this. So, each roller can be rotated, or you can move this back and forth, and the rollers can be, one of them can be rotated, other ones rotation will be automatically fixed. So, maximum freedom possible for this is 2. We can go to nail clipper, again all the information is there, you can go through it and count for yourself, and then see that when it shows that degrees of freedom is 1 for a nail clipper, that means it is actually a well designed one, because you apply the force here, your nail is here to clip, and that is how it works. It deterministic motion even though it has elastic segment here. What segment compliance you have to take here? If you notice, we have taken it to be 1, NSC 1, because this particular segment in a nail clipper only bends, it does not stretch, it does not bend in a way that between the 2 bodies it connects, it does not create x and y motions independently. Okay. So, that segment compliance 1, that comes with practice. When you try various examples, you can use the correct segment compliance, but when in doubt, take the full one. In 2D it is 3, 3D it is 6, and then try to interpret in what ways elastic segment is deforming. So, the main points of this is that both in 2D and 3D we have a formula which gives you again the maximum degrees of freedom possible for a compliant mechanism, and we need to understand this concept of segment compliance, there are two conditions in which we have to use this segment compliance, that it needs interpretation, and assume 3 when you are in doubt in 2D, assume 6 when you are in 3D. So, this interpretation is one way, and the other way is assume the maximum and then interpret what comes out. Like in a, if I have a spring that we took, we know that spring only stretches this way or that way, that is 1 degree of freedom, does not bend. Then if you can interpret right away, you take segment compliance 1, 2, 3 in 2D or 1, 2, 3, 4, 5, 6 in 3D. When you are in doubt, take the full one and then interpret when you get the degrees of freedom for the mechanism, as we have done in a few examples in this lecture. Next important concept to note is this virtual rigid segment. That also has two conditions. One is that whenever there is a force or a moment introduce the virtual segment. If we can apply a force and elastic segment, then you can apply a force in the other direction as well as a moment. The degrees of freedom exist, but you are not exercising. You do not have to, because again the formula gives you the maximum degrees of freedom possible for a compliant mechanism. Okay. So, having a VRS at a point where there is a force or a moment enables you to interpret degrees of freedom properly, and then you would also use a VRS when two elastic segments meet. We have taken an example to illustrate that. Okay. You can also take a VRS when a elastic segment connects to a rigid segment, but mostly will be unnecessary. When you do that, you will introduce a fixed connection and a segment. So, the segment is 6 with a positive, fixed connection with the negative. So, they both cancel, it does not hurt you. It will become clearer for you. So, when you are first practicing, you try to take a VRS when a elastic segment connects to a rigid segment, but that is not really needed. But if it helps you, you can take, but certainly we need to have a VRS when two elastic segments meet, as we have seen in the example. So, to recap, we can interpret degrees of freedom for compliant mechanisms by extending the Grübler's formula that we are very familiar with in rigid body linkages. The additional terms are this elastic pairs and then the fixed connections and the most important segment compliance. Okay. And interpretation of segments as opposed to just bodies, segments includes both rigid as well as elastic ones. If you want to know more about this, there is a paper that we made available as supplementary material for this lecture, which includes a number of case studies. We have used some of those case studies in this lecture, but there are many more examples in that, and the references that are there, which was what was done by Professor Ashok Mida and his students, where they had defined the concept of segment compliance, degrees of freedom. What this a note of this paper says is how to apply those concepts to several compliance mechanisms that we see around us. In fact, after listening to this lecture and reading this paper and the papers that are cited in this, we will be able to interpret degrees of freedom without any doubt for any compliant mechanism, and that will be the most important thing for us to design compliant mechanisms or even analyze them, because without knowing degrees of freedom, it will be very difficult to understand the determinacy of the motion that mechanisms have. Okay. Thank you.